Good morning, Coranda. Good morning. So you please kindly confirm audio, video, and screen once. Please kindly confirm audio, video, and screen. Clear? Yeah. So see, yesterday we discussed about a condition that ZL less than ZC. ZL less than ZC, where I said that if ZL is low in number, obviously loading on the transmission line will be greater compared to SA. For example, if you take up a situation where ZL is greater than ZC, let us say ZL greater than ZC, then what will happen? If ZL is more, means this denominator is more, loading will decrease. Loading will decrease compared to what? SIL. So I can say loading will be definitely less compared to SIL. See, as and when the load impedance is greater or loading is less, load impedance is greater or loading is less, current in the transmission line will decrease. Whenever current in the transmission line is decreasing, compared to ZL equals to ZC condition, definitely half LA square will come less compared to half CV square. I square XL will be less compared to V square by XC, and Q net will become negative, and transmission line is going to act as source of reactive power. Line is going to act as source of reactive power. Those are the comments we are going to make for a condition of ZL greater than ZC. Okay, so I will be taking these slides to the end. Just I will take that modification. So this is the condition of ZL greater than ZC. ZL greater than ZC we are discussing. So whenever the ZL value was greater, so ZL is high we are saying now. So ZL is high means loading will be definitely less, we can say. So I can call loading less than SIL. Loading less than SIL. So as a loading is less than SIL, loading is less than SIL, current in the transmission line will increase, sorry, will decrease. So you can say simply decreases. Decreases. Compared to ZL equals to ZC condition. Compared to ZL equals to ZC condition. Okay. So as and when that loading is less, we can say current is less, already we have mentioned. Yeah, so you can observe now. So half LI square will be less compared to half CV square. I square XL will be less compared to V square by XC. And I square into XL minus V square by XC, this number will come to be negative. This number will come to be negative. So the transmission line will act as sink of reactive power. Sorry. Now it is going to act as source of reactive power. Transmission line will be acting as source of reactive power. Because absorption is coming negative now. Absorption is coming negative means line is going to act as source of reactive. Now, if you take up the two-port network model, what we have drawn, this one, two-port network model, if you take this one, right? Same thing I am repeating. Same thing I am repeating now. So just observe. Just observe here in this case. See, you know already ZL is greater than ZC we have mentioned. ZL is greater than ZC. So Q load is 0. It is not going to absorb any reactive power. So cos phi r equals to 1. But whatever the line we have, that line will be absorbing negative reactive power. Line is absorbing negative reactive power. So transmission line is absorbing negative reactive power. Means line is supplying, source is supplying negative reactive power. Source is supplying negative reactive power means source will be absorbing that reactive power. Source will be absorbing that reactive power. Okay. So as a whole, effective load, if we talk, effective load that is delivering the reactive power, that effective load, whatever we have here, that is delivering the reactive power. So obviously the nature of this effective load will be capacitive. nature of that effective load will be capacity. Nature of the effective load will be capacity. So as the effective load is in capacitive nature, effective load is in capacitive nature, the source has to deliver a leading current. Source has to deliver a leading current. Leading current. So obviously power factor of source will be less than 1 and that will be leading in nature. That will be leading in nature. Okay, and obviously you can observe here ZC by ZL value will be less than 1. ZC by ZL value will be less than 1, we can say less than 1. Yeah. So this is a slide with what we have started. Same as ZL less than ZC, just an extension. Just an extension for that. That's it. Only current value in the earlier case is high because of high loading. But now the current value is less because of low current. Half L A square will come less compared to half CV square. I square XL will be less compared to V square by XC. Then net absorption will become negative. So line is absorbing negative reactive power, means it is not absorbing the reactive power, it is going to deliver the reactive power. So the line is going to act as source of reactive power. Okay. So line is acting as source of reactive power means line is delivering reactive power. Means if we talk about this effective load, this effective load is delivering the reactive power. So the effective load is in the nature of capacity. Effective load is in the nature of capacity. Okay. So obviously, as it's a capacitive load for you, capacitive load, it will be drawing leading current. Capacitive load means it will draw the leading current. So I have shown the source current as leading, and obviously you are going to get the source power factor as leading. Source power factor you are going to get as leading. Okay. So now what will happen to the receiving end voltage compared to sending end voltage in the receiving end voltage compared to sending end voltage? Just you observe here now. This is the equation we have written yesterday. This is the equation we have written yesterday. And how is the value of ZC by ZL? Less than 1 now. See, if the ZC by ZL number is less than 1, just observe now. Less than 1 square. Less than 1 square into sine square beta L plus cos square beta L. This whole number will be less than 1. This whole number will be less than 1. So under root of that, less than 1 will be that less than 1 into VR is equals to Vs. So definitely Vs value will be less compared to VR, you can say. Mod Vs value will be less compared to mod VR, we can say. Right. So in this situation, you can observe that as ZC by ZL number is less than 1, you can observe that sending end voltage will be less compared to receiving end voltage, or in reverse, receiving end voltage will be greater compared to sending end voltage. Receiving end voltage will be greater compared to sending end voltage. And if you calculate current, and your receiving end current definitely comes less compared to sending end current by going to the equations. If the receiving end current will be definitely low compared to sending end current. What we are going to say this effect, if this mod VR value means receiving end voltage magnitude greater compared to sending end. Receiving end voltage magnitude was greater compared to sending it. What we are going to say this one? This we will call as Ferranti effect. This we are going to name as Ferranti effect. That we call as Ferranti effect in the transmission line. Ferranti effect in the transmission. Yeah, could you please tell me now? Could you please tell me when we are going to get this Ferranti effect in the overhead lines? When we are going to get this Ferranti effect in the overhead lines? You know, we discussed about the Ferranti effect long back, maybe in case of medium transmission lines and all. Yes or no? Right. Under what conditions we are going to get this Ferrand effect? Under light loading conditions, or you can say no load condition. Under no load condition as well as under light loading conditions, we are going to get them. What do you mean by that lightly loaded transmission line? What do you mean by that lightly loaded transmission line at which we are going to get the Ferrand effect? Means that's a line which is loaded for a loading less than SIL. That's a line loaded for loading less than SIL. So loading less than SIL can be treated as a lightly loaded operation. Lightly loaded operation at which we can achieve or we are going to get receiving end voltage magnitude greater compared to sending end voltage magnitude. Sending end voltage magnitude. All of you getting these words what I am saying you? Right. So Ferrand effect, you can write here, occurs for a simple condition of loading less than SIL. Loading on the transmission line less than the surge impedance loading. At that condition, we are going to get it. Okay, next thing. Next thing. All of you listen to me. All of you listen to me. This is one general statement I want to tell you. We have to remember this as well as it has to give a more clarity. It has to give a more clarity to you. For example, we have a transmission line operating under no load condition. We have a transmission line operating under no load condition. So the circuit might be approximately taken something like this. Approximately, it's not exact equivalent circuit of line. This is approximate equivalent circuit of line, something like this. I'm taking. Okay. Right. Just observe, observe please, observe. So this side, we are keeping on AC voltage source, having some sending end voltage Vs, and we have some sending end current as Is. And it's a no load side, no load. So IR is equals to 0. And you have voltage as VR. No load voltage anyhow, that I'm saying as VR. No load voltage, I'm saying it as VR. All of you please tell me, all of you please tell me, please tell me. How is this VR magnitude compared to IR? Sorry, Vs. How are this VR magnitude compared to Vs? Definitely greater. Definitely greater. Because of no load operation, you know that mod VR will be greater compared to mod Vs. Nobody is responding. What happened? Yes or no? As we are saying, it is under no load. Definitely, mod VR value will be greater compared to mod Vs. Mod Vs. Okay. Okay. I am asking one more simple question. Simple question. How is the value of mod IR compared to mod IS now? How is the receiving end current compared to sending end current? See, definitely sending end side we have some current, right? Definitely we are going to get some non-zero current at sending end side, but receiving end current is 0. So definitely IR will be less compared to IS. IR will be less compared to IS. Okay. Just look in the view of the long transmission line, distributed model, starting from sending end side, towards the receiving end side, What is happening to current value? Towards the receiving end side, what is happening to the current value? Decreasing. Starting from sending end side towards the receiving end side, current is decreasing. What is happening to voltage value? What is happening to the voltage value starting from sending end side to receiving end side? It is increasing. Voltage value continuously increasing. Okay, so in the transmission line, in the practical transmission lines, right? If one quantity means voltage and current we are discussing now, voltage and currents. If one quantity starts increasing, definitely other quantity starts decreasing. If one quantity starts increasing, definitely other quantity starts decreasing, we can say. Means if voltage magnitude starts increasing, current magnitude starts decreasing. Else in reverse. If voltage magnitude starts decreasing, current magnitude starts increase. This will happen always in the transmission lines. If you don't have any change in the voltage magnitude, you don't get any change in the current magnitude also. Like for the case of loading equals to SIL. For the case of loading equals to SIL, I don't have any change. in the voltage magnitude, so that I don't have any change in the current magnitude also. Okay. Yeah. Next thing. So let's have a small conclusion as a comparison between the three cases, whatever we have studied now, in the three cases. So I'm saying here, loading equals to SIL. Loading equals to SIL here. And here I'll say loading greater than SIL. And the last one is a loading less than SIL. Loading less than SIL. Kindly adjust with this corner term. What I'm writing here, loading less than SIL. Loading less than SIL. Loading equals to SIL, right? And loading greater than SIL, and then loading less than SIL. Yeah. So kindly tell me, ZL compared to ZC in all the three cases. Else, first let me complete for loading equals to SIL. ZL is equals to ZC. ZL is equals to ZC. No, here ZL and ZC values are equal. Next thing, receiving and sending end voltage magnitudes are equal. So we have mod VR equals to mod VS, as well as mod IR value is also equals to mod IS. So what's the angular difference between the lines? Yeah, tell me, what's the angular difference between the sending end and receiving end voltages? Delta, that is equals to beta L. Already we have discussed, right? Delta is equals to beta L. These are some points we have for the condition of loading equals to SIL. Next, you tell me please. What is the behavior of transmission line? What is the behavior of transmission line? It will be acting as a flat line. I think we have discussed about that in the yesterday class. Flat line, yes or no? Voltage magnitude throughout the length of the line will be same. Not only that, current magnitude also same throughout the length of the transmission line. That line is going to be called as flat line. Okay, line is a flat line. Is it lossless? All of you please tell me, is it lossless line? Line is a flat line. Okay, is it a lossless line? Yes. So the line is a flat line, and of course it is lossless. Okay, what is a transmission line behavior with respect to reactive power? What is a transmission line behavior with respect to reactive power? It will be acting as neither sink nor source of reactive power. Line is neither sink nor source of reactive power. Neither sink nor source of reactive power. Neither sink nor source of reactive power. Okay? Neither sink nor source of reactive. Let's think about loading more than SIL and less than SIL quickly. So loading more than SIL, ZL will be less compared to ZC. ZL will be less compared to ZC. And how is your receiving end voltage? That is less compared to sending end voltage. And if you take up the receiving end current IR, that is greater compared to sending end current IS. But you know that the angular difference between the receiving end and sending end side voltages. The angular difference between the receiving end side and sending end side voltage will be greater than beta L. Loading is more. Angular difference between the voltages will also become high. Angular difference between the voltages will also become high. So delta will be greater than beta L value. Okay, next thing. You think about this also quickly. ZL greater than ZC case it is. And receiving end voltage will be greater compared to sending end voltage value. Receiving end current will be less compared to sending end current value. And the delta will come less than that beta L. Delta will be coming less than beta L. Delta will be less than beta L. Yeah. So once after completion, please let me know. Please raise your hands. I will proceed with the next terms. Next term is very important to understand. Exactly. Next term is very important to understand. Okay, listen now. Listen please. Loading more than SIL. Mod VR is less compared to mod VS. Can we call this line as a flat line? loading more than SIL, mod VR is less compared to mod VS. Can we call this line as a flat line? No, we can't call it. We can't call that line as flat line. Okay, fine, that's okay. It's not a flat line, but is it a lossless line? It's not a flat line. Okay, is it a lossless line? Yes or no? Yes, yes. See, the thing what you have to understand here is line is lossless. Line is lossless. How in the sense? We have taken lossless line equations only now. We have taken the lossless line equations only. So line is lossless, but it is not a flat line. But it is not a flat line. That's the point what you have to understand carefully here. Right? So line is lossless. Line is lossless, but not a flat. But not a flat. But not a flat line. What about the other one? Other. Is it a lossless line? In the second case, yes, line is lossless, and again, it's not a flat line. So line is lossless. Line is lossless, but not a flat line. But not a flat line. So what is the behavior of this line with respect to reactive power in this case of loading more than SIL? For loading greater than SIL, loading greater than SIL. Tell me please, what's the behavior of line? Line will be acting as sink of reactive power. Line acts as sink of reactive power. And whereas in this case, line acts as source of reactive power. Source of reactive power. Transmission line is going to act as source of reactive power. Source of reactive power. Now, let's think about that loading more than SIL, loading less than SIL particularly. Just I will be showing that voltage profile. How that voltage is changing starting from sending end side to the receiving end side in a plot. So let's take up that. Let's take up that. See this. This is the line length axis, you can call line length axis. And it's a voltage magnitude axis. Okay. So voltage magnitude axis. And it's the X, I can say line length axis. Same thing I will repeat for the, okay, let me show that flat voltage and all, then I will repeat it. Look here. This is the sending end side location, and this was the receiving end side location. Sending end side, and I am showing that as a receiving end side. Sending end side and receiving end side. Okay, so observe. So I am showing one dotted line here. Just for reference line is that. And I'm showing one line to indicate this as a flat. To indicate this as a flat. That else you can call this is the sending end voltage magnitude point. Sending end voltage magnitude point. This point we are calling as sending end voltage magnitude point. And how is the receiving end voltage? That depends upon the loading. That depends upon the loading. Okay, I will copy this diagram. Same diagram, I will repeat to the other side because we have to discuss about two types of loadings here. That's why I'm repeating that same diagram on the other side also. Okay. And please draw these two things quickly. In the first case, we are going to exhibit a condition of loading greater than SIL. Okay. And in the second case, I am going to exhibit a condition of loading less than SIL. First case, I am going to exhibit loading greater than SIL. Second case, I am going to exhibit the loading greater than, so less than SIL. These two. Yeah, once after completion, please raise your hands. I will show the plots. Okay. Look at the first one. See, in case of loading greater than SIL, loading greater than SIL, your receiving end voltage magnitude is low compared to sending end voltage magnitude. So this point, it is the receiving end voltage magnitude mod VR. And how is it voltage starting from sending end side to receiving end side? Means it is continuously decreasing. Starting from the sending end side to receiving end side, voltage will be continuously decreasing. Strictly speaking, all of you listen. Strictly speaking, it will be definitely a non-linear. Strictly speaking, it will be definitely a non-linear shape, non-linear shape. But as an approximation, I'm showing this as a simple straight line. I'm saying again, it's not a straight line, strictly speaking, right? I'm showing approximately in this manner. That's the way how that voltage is decreasing towards the receiving end. And in this case, right, voltage is increasing starting from sending end side to receiving end side. Voltage starts increasing from sending end side to receiving end side. Something like this, you can say. Something like this, you can say. Voltage is increasing towards the receiving end side, starting from mod Vs to the value of mod Vs. The value of mod Vs. Okay, next. Listen, please. Listen, please. All of you, listen. All of you, listen. VR is not equals to Vs. That's okay. How to make that VR equals to Vs now? How to make this receiving end voltage magnitude to be equals to sending end voltage? Anybody? Anybody tell me please. How to make? So this is a source location, you can say, and it is your load location. This is the transmission line. This is the transmission line. Starting from source location towards the load location. Towards the load location, we have plotted that voltage profile. That voltage profile. We are getting like that. So it's a load for which it's a light load, loading less than SIL, and here the loading is greater than SIL. Yeah, I'm asking you the same question. I'm asking you the same question. Without modifying this load, please listen. Without modifying this load, loading will be greater than SIL. I'm not going to disturb the load value. I'm not going to disturb the load value without disturbing the load value. How to make up this VR value to be equals to Vs? How to make up the VR value to be equals to Vs? We have to keep the shunt capacitor bank. Shunt capacitor bank. Yes or no? Right. So I was interested to keep one shunt capacitor bank at this bus. Like this. I am keeping the shunt capacitor bank at the receiving end side. At the receiving end side, such that this receiving end voltage magnitude to be equals to sending end voltage magnitude. It's a new value after keeping the capacitor bank. After keeping the capacitor bank. So I'll write here. To make mod VR is equals to mod Vs. A shunt capacitor bank has to be kept at receiving end side. Has to be kept at receiving end side. Has to be kept at receiving end side. Okay, so in the similar way, here, in order to make this VR value to be equals to Vs, so it's a VR new, I'm calling. So I have to keep one shunt reactor bank at the receiving end side. Keep one shunt reactor bank at the receiving end side. Okay, so in this case, to make VR equals to Vs, make that mod VR value to be equals to mod Vs. A shunt reactor bank shall be kept. Shunt reactor bank has to be kept at receiving end side. Has to be kept at receiving end side. has to be kept at the receiving end side. So all of you getting this? Yeah. You see, in the first case, we are keeping shunt capacitor bank here. Second case, we are keeping shunt reactor bank. That's okay. We are making mod VR equals to mod VS. How will be the voltage throughout the length of the line now? Mod VR equals to mod VS is okay. I am asking you now, how is the voltage throughout the length of the line? Will it be equal or unequal? Voltage. Voltage, it will be definitely unequal, right? Definitely unequal. It won't be same. It won't be same, right? It won't look like a flat line. It won't look like a flat line. See, look here, please. Starting from the sending end side, voltage starts decreasing. Voltage starts decreasing. Okay. And beyond certain point, voltage will start increase and then touches the value of Vs. So this is the red color voltage profile we are going to get after keeping the shunt capacitor bank. So this is with the shunt capacitor bank. With the shunt capacitor bank. And this blue color is without shunt capacitor bank. And here also. Starting from sending end side towards the receiving end side, voltage starts increase in the similar way. Voltage starts increase, but beyond certain point, voltage will start decrease and touches the value of Vs, which is nothing but this new voltage what we have mentioned. So this is with the shunt reactor. With the shunt reactor tank. With the shunt reactor. Okay. With shunt reactor. So like this, we are going to get the change in the voltage profiles after keeping shunt capacitor bank, as well as after keeping the shunt reactor bank. Done. I will ask one very simple question to you. Loading means power consumed by load only. What's the doubt in that? Yesterday also I said no. Yesterday also I said the same thing. Loading is nothing but what is the amount of power demanded by the. Okay, listen please. See, after keeping that shunt capacitor bank, we are getting mod VR equals to mod Vs. After keeping shunt reactor bank, in the other case, we are getting mod VR equals to mod Vs. Can we call this line as a flat line? After keeping shunt capacitor bank and after keeping the shunt reactor bank, can we call this line as a flat line? Yes or no? Can we call the line as flat line after keeping the shunt capacitor bank and shunt reactor banks? No. What is the definition of flat line? Voltage magnitude should be same throughout the length of the transmission line, but only end voltages are equal, not throughout the length of the line. Not throughout the length of the line. All of you getting? Right. See, actually, this type of compensation what we have provided to improve voltage profile, of course, to improve the voltage profile, whatever the type of compensation we have provided here, it is going to be called as, listen my words, lumped compensation. Lumped compensation. Okay, so lumped compensation means keeping compensator at only one place, keeping the compensator across the load or at the receiving end side. It's a lumped compensation. Keeping compensator at one place. Keeping compensator at one place in bracket, right? Maybe across the load. Maybe across the load. Yeah. Okay. So next thing. So I'll take up in the next slide. I'll tell you. Listen all of you. In the next slide, don't keep any heading. Don't keep any heading. Just listen what I'm saying. Just listen what I'm saying. I'm taking a lossless long transmission line. Lossless long transmission line. Distributed model. To get an understanding. To get an understanding, I will be keeping that series inductive reactance and shunt capacitor susceptance. Listen also. This is transmission line series element. It is a transmission line shunt element. It is a first section of line. Approximately speaking, it is the first section of line. Right. First, second section, and so on. So on. We have n number of sections here. N number of sections. Okay. So this side, I am keeping one voltage source. This side, I am keeping one voltage source, and this side, I am keeping a resistive load, of course. Load, and this was the source. Source location, and this is a load location. All of you listen. All of you listen. Don't write anything. Just listen. See, this per kilometer sections you take, per kilometer sections. This series reactance or series impedance per kilometer will be JX line. Shunt admittance will be JB line. And here also JX line, JB line, and so on. So up to the end. To the end. Okay, yeah. This is a sending end side voltage. We have Vs. Sending end side current I have as Is. Receiving end side voltage, it is VR, and the receiving end side current I have as IR. Receiving end side voltage and current as VR, IR. Sending end side we have Vs, Is. Next thing. Listen up. Very simple. Don't confuse. It's a very simple thing. See, this point I'm standing. What is the voltage here? What's the voltage? By applying KVL, approximately you take KVL. What is the voltage at this place means? It is Vs minus Is into Jx line. Vs minus Is into Jx line is a voltage at this place. How to make or how to maintain this voltage is equal to Vs? How to maintain that voltage is equal to Vs? Actually, equation for Vs is, this point voltage, the point voltage is Vs minus Is into Jx line, I said now. Vs minus Is into Jx. How to make this voltage as Vs only? How to kill this second term? How to kill that second term? Anybody tell me please? Anybody please tell me how to do that? For that purpose, I will be adding one series capacitor. Okay. And how is the impedance of the series capacitor? Plus J or minus J? How is the impedance of series capacitor? Plus J or minus J? Minus J. So I'm calling it is minus JXC. Now what you do is you try to match this XC value equals to X line. Try to match this XC value equals to X line so that overall series impedance will be 0. Overall series impedance is 0 means this node voltage will be as it is of Vs. Okay, next thing. Look here. This is sending and current Is. In that, some current is drawn by this JB line. Remaining current will go out. See, whatever the current going out, that I should make as Is. Okay. See, making that as IS, how in the sense, we will be adding one shunt reactor bank. In this place, we are going to add one shunt reactor. How is the admittance of shunt reactor? How is the admittance of shunt reactor? Is it plus J or minus J? Admittance of shunt reactor will be minus J. So it will be minus JBR, minus JBR. And you try to match that BR and B line as equal. BR and B line as equal. So that overall admittance will be zero. Overall admittance will be zero and outgoing current will be exactly equals to IS. Outgoing current will be exactly equals to IS. All of you getting this? All of you getting this? What I am saying? Yeah, nobody is responding. Is it clear? Like that, like that. For each and every kilometer length, I will be keeping one series capacitor and I will be keeping one shunt reactor. Series capacitor we are keeping to cancel the series inductive reactance. Shunt reactor we are keeping to cancel the shunt capacitor reactance effect. Like this we are showing. Right? Ultimately, after reaching to the end, you will be getting this voltage as a Vs and current as obviously Is. After reaching to the end, we are going to get the voltage and currents as Vs and Is, which are exactly equals to VR IR. Which are exactly equals to VR and IR. Okay. Yeah. Next thing. Please listen. What are these red color elements? I need your answer. What are the red color elements? External elements we are adding. External series capacitor shunt reactors we are adding to the line. What about these black color elements here? What about these black color elements? Black color elements are natural elements which are not visible. Black color elements are natural elements which are not visible for us. Okay. See, for example, if you talk in the view of the practical transmission line, listen all of you. This is a practical transmission line wire, you can say, having certain length. Just look. Having certain length, I'll tell you. Total length of line, let us say 300 kilometers. 300 kilometers. Now I'm making this into let us say 6 sections. Six sections. Look please. Like this, we are making number of sections. 6 sections I am taking. Section 1, 2, 3, 4, 5, 6. So each section length is 50 kilometers. Each section length is 50 kilometers. 50. See, listen. Look, please. At the end of this 50 kilometer, I will keep one series capacitor and I will keep one shunt reactor, something like this. Such that this series capacitor should cancel the whole 50 kilometers length series reactors. Series capacitor should cancel whole 50 kilometers length series reactors. Shunt reactor, what we kept there? Shunt reactor. It should cancel the shunt admittance of that 50 kilometers length. Shunt admittance of that 50 kilometers length of line. All of you getting me? Yeah. So like this. At this point also, I will be keeping same. At this point also, I will be keeping same. So at the end of each 50 kilometers length, I will be keeping an arrangement something like this. Right. This is going to be called as distributed compensation. Yes or no? This is going to be called as distributed compensation. What the compensation we said earlier? That is a lumped compensation I have mentioned. And this type of compensation will be termed as distributed compensation. Distributed compensation. So this heading, what we are going to take here is distributed compensation. Yeah, if you are writing it, please complete quickly. Please complete quickly if you are writing. distributed compensation. So once after completion, please raise your hands. I will be discussing about this further. I will be discussing about this one further. Okay, good, good. Now what I can say is to cancel the effect of series inductive reactance and shunt capacitive reactances. To cancel the effects of the series inductive reactance and shunt capacitive reactances, we are going to add series capacitors and shunt reactors at regular intervals of the transmission line. At regular intervals of the transmission line. By doing that, we are going to get VR equals to Vs, IR is also equals to Is. Okay, right. I can say cancel the effects of natural series inductance or inductors or inductances and shunt capacitances of line. Some external series capacitors and shunt reactors will be added at regular intervals intervals of line at regular intervals of line. This process is called as tuning of the transmission line. This process is called as tuning of transmission line. Tuning of the transmission line. Yeah, you see, by tuning process, yeah, you see, we will be getting voltage magnitudes almost constant throughout the length of the line. Current magnitudes also constant throughout the length of the line. Yes or no? Voltage magnitudes are constants throughout the length of the line. Current magnitudes also almost constant throughout the length of the line. Can we call this line as a flat line? Yes or no? No, we should not call this line as a flat line. What is the definition of flat line we have taken? What is the definition of the flat line we have taken? Flat line in the sense that's a line which have mod V and mod values as same throughout the length without keeping any extra element, without placing any extra element. If you get that behavior, then the line is going to be called as flat line. But now we are providing some compensation. To meet that requirement. This line cannot be called as flat line. This is going to be called as tuned power line. This is going to be called as tuned power line. Okay. So by tuning process, V and I are same throughout the length of the line. Throughout the length of line. The line is called as flat line, tuned power line. It should not be called as a flat line. Flat line behavior will come without keeping any extra elements if we get voltage magnitude same, current magnitude same throughout the length. After keeping any extra element, if you're getting that behavior, the line is called as tuned line. Only one meaning, one simple way of saying. Flat line will exist only for ZL equals to ZC. Only for the ZL equals to ZC, the flat line will be exist. So see, whenever you are providing this distributed compensation, definitely there is a change in the series impedance of the network, as well as there will be a change in the shunt admittance of the network. Series impedance of the network will change. Shunt admittance of the network will also change. See, providing compensation for whole reactance, whole susceptance, it's not suggestible because of resonance things at all. For example, if you match this X line with exactly equals to XC, B line and BR as exactly equal, there's a problem of the resonance. There's a problem of the resonance. All of you getting my words, please? All of you getting my words? So I was not interested to provide. Look to me. Yeah, look at this one. Look at this. See, if you are providing this X line exactly equals to XC, means XA exactly equals to X line, there's a problem of resonance. So we are not interested to provide compensation for complete series inductive reactance as well as complete shunt capacity susceptance. Following. So we will be providing some degree of compensation. Some degree of compensation only we are going to provide from this point onwards. So I was taking up in two cases here, two cases. By providing these series and shunt compensations, definitely there is a change in the series impedance per kilometer. There is a change in the shunt admittance per kilometer. Series impedance, shunt admittance, these values are going to change. On the behalf of that, there will be a change definitely in the value of ZC, surge impedance, that's going to be changed. As well as there is a change in the value of gamma, propagation constant, that is also going to be changed. These changes we are going to discuss with compensation in comparison without compensation. In comparison with without compensation. So I will be taking up here, without compensation. Without compensation. Without compensation. Okay, without providing any compensation, series impedance per kilometer is JX line. Shunt admittance per kilometer is JB line per kilometer. Okay. What is ZC? I'll say ZC1, surge impedance, which is square root of small z by small y. Na? J and J will be cancelled out by taking up that ratio. So it will be square root of X line by B line. That's the ZC1. Okay. Next, I'll take beta. Rather than gamma, I'm taking beta because you don't have any real part, right? Don't have any real part. So I'll say beta. Phase constant. It will be root of X line into B line. I think I have discussed about this formula already. How you get that root of X line into B line? That I think I have discussed. Yeah. Yeah. Good. Right. Next, with compensation, I will write with distributed series and shunt compensations. Series and shunt compensations. With the distributed compensation. Distributed compensation. With the distributed compensation. What is the series impedance Z? You can write. Series impedance Z will be JX line minus JXC. So you can call this is J X line minus X. And what will happen to Y here? J B line minus BR. J B line minus BR. J X line minus XC. And then we have J B line minus BR. And if you take up ZC here, I'll say it is ZC2. ZC2. It becomes square root of X line minus XC in the numerator. Denominator will be B line minus BR. denominator will be B line minus B. XC2, new surge impedance. After providing compensation, that's the new surge impedance formula. Root of X line minus XC. JJ will be cancelled. Z by Y, JJ will be cancelled. That's why I'm not showing it. Okay. Next. So see, this I am going to write it as square root of. In the first numerator, X line is common. So it is 1 minus XC by X line. By B line is common in the denominator. You write it as 1 minus BR by B line. BR by B line. 1 minus XC by X line. Next in the denominator, 1 minus BR by B line. See that XC by X line, I am going to name it as degree of series compensation. Degree of series compensation. BR by B line, we will be naming it as degree of shunt compensation. XC by X line, we are calling as degree of series compensation. Degree of series compensation. I'll take it as KSE typing. KSE. And the other term, BR by B line, it will be called as degree of shunt compensation. Degree of shunt compensation, we name this as KSH. KSH. Degree of shunt compensation, we are naming it as KSH. KSH. And sometimes we say percentage series compensation, percentage shunt compensation. That is simply KSC multiplied with 100%, KSH multiplied with 100%. Okay, if you want, I'll write quickly. Percentage series compensation. XC by X line value, what we have, so called KSC into 100%. Percentage shunt compensation. So it will be BR by B line into 100%. BR by B line into 100%. Percentage shunt compensation, percentage series compensations. Yeah, so let's continue. Let's continue with this. So I can rewrite this ZC2 here, ZC2 further. Yeah, please kindly raise your hands after completion. Please kindly raise your hands after completion. Okay, good. So I'll say ZC2 will be equals to, you can have root of X line by B line, one term. That is nothing but ZC1. Root of X line by B line is ZC1. ZC1 into, you have already square root of 1 minus degree of series compensation by 1 minus degree of shunt compensation. ZC2 is equals to ZC1 into square root of 1 minus KSC by 1 minus KSH. Okay. Similarly, what is beta 2? What is beta 2? Beta 2, we have to say. Beta 2 is equal to square root of X line minus XC, and you have here B line minus BR. B line minus BR. So if you rewrite this in a simplified way, you get this like beta 1 into square root of 1 minus KSE, and it is 1 minus KSH. So it is beta 2. Beta, right? Phase constant beta. Phase constant beta. So I think all of you getting this. Yeah. So this topic is also very important for examination. that is the distributed compensations, series and shunt compensations to the transmission line. Transmission. All of you understood the difference between distributed compensation and lumped compensation? See the can say power transfer equations. Power transfer equations, we have discussed some problems, right? Keeping a capacitor bank to maintain the voltage as 275 kV at both sides or 1 per unit at the both sides. What is that compensation we discussed? What is that compensation we discussed? Anybody? The power transfer equations, we discussed some problems of finding the rating of capacitor bank. Finding the rating of capacitor bank. What problems those are? Lumped. Those are lumped compensation problems. But now we are discussing about a term like distributed compensation, providing the compensation throughout the length of the transmission, throughout the length of the transmission line. But anyhow, most practically, lumped compensation will be used. Lumped compensation will be used most practically. Distributed compensation also they will use. Distributed compensation also they will use. May not be cutting this length into 50 kilometers. They may go for 100 kilometers or they may go for 150 kilometers. Okay, series capacitors are practical. Shunt reactors also practical in the system. Okay, fine. Next, let's do some problems in this quickly regarding this compensation. Regarding this compensation, I'm going to take up some problems. Yeah. See this one. It's a previous gate examination question. Previous gate examination. Just go through it. Yeah. Since a lossless transmission line, having surge impedance loading of 2280 megawatt. 2280 megawatt. A series capacitive compensation of 30% is placed. Series capacitive compensation of 30% is placed. Then SIL of the compensated transmission line will be how much? SIL of the compensated transmission line will be how much? Yeah, tell me please. Simple, very simple. So actually, without providing any compensation, SIL value is given 2280 megawatts. 2280 megawatts. I'll say it's a SIL1. SIL1, which is nothing but V square by ZC1. Without compensation, it will be V square by ZC. After providing compensation is 30% compensation. I'll write with 30% series compensation. 30% series compensation. Okay. 30% series compensation means degree of series compensation is 0.3. Degree of series compensation is 0.3. Anything mentioned regarding shunt compensation in the problem? Anything mentioned regarding shunt compensation in the problem? No. It didn't mention anything about shunt compensation, so KSH will be 0. No shunt compensation, so KSH will be 0. Now, according to this, surge impedance is going to be modified. According to that surge impedance modification, SIL value is going to be modified. So let's see. Surge impedance with compensation ZC2 equals to ZC1 into square root of 1 minus KSC by 1 minus KSH. So you can call this one ZC1 into square root 1 minus KSC, 1 minus 0.3 by 1 minus KSH is 0. So you get this like root 0.7 times of ZC. Root 0.7 times of ZC1. Now, what is the surge impedance loading? 2, you can say. Surge impedance loading 2 is V square by ZC2, V square by ZC2. And it will be coming like V square by ZC2 is root 0.7 times of ZC1. Root 0.7 times of ZC1. What is V square by ZC1? V square by ZC1 is a value SIL1. V square by ZC1 is the value SIL1. So I can call SIL2 is equal to SIL1 by root 0.7. SIL1 is 2280 and in the denominator you get 0.7 under root. This, if you calculate, you may get like 2725 megawatts. 2725 megawatts. After providing series compensation of 30%, we are getting this SIL value like 2725 megawatts. 2725 megawatts. Yeah. Next. So let's see one more problem if possible. One more problem. So you see this question, no? See this question. All of you listen to this. See, before moving to this question, before reading this question, just listen my words. Listen my words, please. This is a long transmission line wire we have. Let's say long transmission line wire. We are keeping some load at the receiving end side with a load impedance of ZL. And surge impedance of this line is ZC. All of you listen, please. All of you listen, please. See, this ZL is not equals to ZC. ZL value is not equals to ZC. So that this receiving end voltage value will not be equals to sending end voltage. Concentratedly listen here. Concentratedly listen here. ZL is not equals to ZC. So obviously VR value is not equals to VS. Now the question what I am asking is how to make this VR value equals to VS. How to make that VR value equals to VS. What we have to make. What you have to do. What you have to do. What you have to do to get that VR value equals to VS. Anybody? Tell me please. Tell me please. What you have to do. One option. Listen please. Listen please. One option is keeping a capacitor at this bus. Keeping a capacitor at this receiving end bus. That's one option. Other option, modify the value of ZL to be equals to ZC. Modify the value of ZL to be equals to ZC. See this, to make mod VR is equals to mod VS. First option, what you said? First option, what you said? Keep shunt capacitor at receiving end side. Shunt capacitor at receiving end. Next, second option, what I am saying? Modify ZL. Modify ZL to be equal to ZC. To be equal to ZC. What's the third option? Anybody? What's the third option? Third option. Third option is what? Modify the value of ZC to be equal to ZL. ZC you have to modify that such that the ZC value to be matched with ZL. Modify ZC to be equal to ZL. To be equal to ZL. See, first one will fall in the category of lumped compensation. Second one will fall in the category of modifying the load itself. Modifying the load itself. Second one. Third one, falling in the category of distributed compensation. By providing the distributed compensation, we are capable to vary the surge impedance of transmission line that we try to match with the load impedance. In order to achieve the flat voltage profile. I think all of you getting this clarity what I have discussed here. I don't know whether you have understood this or not. All of you getting clarity about it? Nobody is responding. Okay. Good. So now let us see this problem what I have given. Just observe this problem what I have given. Look this problem. See, a long transmission line has a surge impedance 300 volts at a rated voltage of 400 kV. Okay. If the load kept at the receiving end side is 400 megawatts UPF, 400 megawatts UPF, find the nature and degree of compensation to be provided for the line to maintain flat voltage profile. What is the nature of compensation to be provided, as well as what is the degree of the compensation to be provided. First, we should decide, is it to be series compensation or shunt compensation? That we have to decide first. After that, we should tell what is the degree of the compensation to be kept. Okay, so let's continue in the next slide with this one. How to decide which nature of compensation to be placed? Anybody? How to decide which nature of compensation to be placed? We have to compare the loading value with SIL. Okay, what is the loading on line? 400 megawatts. Loading on the line is 400 megawatts. And what is SIL? Rated voltage square by ZC. Let me tell in the solution. Loading on the transmission line is equal to 400 megawatts. Of course, it is at UPF. Of course, it is given at UPF. Okay. So surge impedance loading is equal to, already we have mentioned it, rated voltage line to line square by surge impedance. Rated voltage line to line square is 400K whole square. And surge impedance, he said it is 300. So it will come in megawatt. How much? How many megawatts is that SIL? How much is that? 533.33. This number is 533.33 megawatt. His observation is now the loading on the line is less compared to SIL. Loading on the transmission line is less compared to surge impedance loading. Means definitely we can experience the receiving end voltage greater compared to sending end voltage. Receiving end voltage will be greater compared to sending end voltage. Okay. Receiving end voltage will be greater compared to sending end voltage. Next thing. Listen to me. See, as and when you say loading is less compared to SIL, your load impedance will be greater compared to surge impedance. Load impedance will be greater compared to surge impedance. Means we have to increase the surge impedance. Value. Increasing the surge impedance means we have to provide the compensation. To how much? To what value we have to do that? Means, right? We should calculate the load impedance with the help of the 400 megawatts by assuming the receiving end voltage as 400 kV. Because in future voltage will be 400 kV only. In future voltage will be 400 kV only. Means after providing the compensation, we get the voltage as 400 kV. That's it. Yeah. So let's see. Let's see. Else you can take up this ratio also. Loading to SIL ratio also you can take. Yeah. Listen please. Listen please. Load impedance ZL. Load impedance ZL approximately equal to, just observe, loading equals to rated voltage square by ZL. So ZL equals to what you can say, rated voltage square by loading. Rated voltage square by loading. So rated voltage square means 400 kilovolt square. By how much is that loading we have? 400 mega. So it will come to be 400 ohms is the load impedance. Load impedance value, it is 400 ohms. 400 ohms. So after providing the compensation, after providing the compensation, new surge impedance required will be equal to new surge impedance required will be equal to what you can say, new surge impedance will be equal to 400 ohms. So as we know already, ZC2 with compensation equal to ZC1 into square root of 1 minus KSC by 1 minus KSH. ZC2 is equals to ZC1 into square root of 1 minus KSC by 1 minus KSH. So now you can take that ZC2 by ZC1 value. One minus KSC by 1 minus KSH. What is that? ZC2 by ZC1? ZC2 number 400 by what is ZC1 number? What is ZC1? ZC1 number is 300 ohms, right? So it will be square root 1 minus KC by 1 minus KSH. So this is 4 by 3. 4 by 3 in the sense you may get like 1.333 here. And it is root 1 minus KSH by 1 minus, sorry, KSC by KSH. 1 minus KSC by 1 minus KSH. Yeah. Okay. Next, listen now, listen. See, this value we should get as more than 1. This value we should get more than 1. So which compensation I should provide among these two? Is it series or shunt? Anyone. For example, if you provide series, then 1 minus some number is less than 1. Root of that is less than 1 only. It's not satisfying the requirement. If you go with the shunt compensation, 1 minus some number, okay, less than 1. 1 by less than 1, that's greater than 1. And the root will be greater than 1 definitely. So I can say to meet above requirement, to meet that above condition, KSC number will be 0, no series compensation, but I have to provide the shunt compensation, particularly shunt reactive compensation. Shunt reactive compensation we have to provide. Shunt reactive compensation we have to provide. So 1.333 is equal to square root of 1 minus KSC by 1 minus KSH. Get this number KSH, how much? Get that value of KSH. Anybody? Tell me the value of KSH. So it will be coming like 0.44 or 43. Is 43% shunt compensation we have provided. 437. 43.75% of shunt compensation we have to provide. We have to assume it Ks is 0. Just by to satisfy this equation, this number is greater than 1, na? Greater than 1. If you take Ks non-zero, then this value will come less than 1, which is not satisfying. So definitely we should go for Ks6. Then only this ratio will come greater than 1 according to the requirement. Fine. Next. So this is one variety of problem we can expect in the compensation. One variety of problem we can experience. So till now we have discussed about different types of loadings, like loading equals to SIL, loading more than SIL, loading less than SIL. These things we have discussed. Okay, after that we discussed about some compensation techniques and all. Now we will be proceeding further. What loading is practical for overhead lines and what loading is practical for the underground cables? Okay, so the next heading is loading on the overhead transmission lines. Loading on overhead transmission lines. Loading on overhead transmission lines. Loading on the overhead transmission lines. Okay, yeah. So let's continue. Let's continue. How to get KSH value means we have to calculate from this. Simple mathematical terms. Simple mathematical terms only. Yeah. Look here. Look here. See, before discussing about loading on the transmission line, compare it to SIL, strictly speaking, compare it to SIL. I should discuss about these two terms too. One is a maximum power transfer capacity. We discussed in ABCD. We discussed that in terms of ABCD, maximum power transfer capacity. That equation I will write. That I will compare with the SIL first. That I will compare with the SIL. Then we will make some comments. Okay. First, anyhow, let me write first. Ideal power transfer capacity, SIL. Ideal power transfer capacity, nothing but SIL only, which is mod V square by ZC. Mod V square by ZC. Next thing. Maximum power transfer capacity. Maximum power transfer capacity. Pmax. You please go with the equation here. P maximum equation. P maximum. In terms of ABCD. Sending end voltage, receiving end voltage by mod B. Cos of beta minus delta will not come. It will be 1 minus. We have mod A by mod B. Mod VR square. Cos beta minus alpha. Get this like cos beta minus alpha. Yeah, please listen. There is a notation problem actually. There is a notation problem here. We have discussed beta at some places, maybe here, right? Beta, this beta. Omega root LC, cos beta L, sin beta L. That beta is a phase constant. But now in the power equation, we are getting this beta. What is this beta? This is angle of parameter B. What is alpha? Angle of parameter A. There's a notation problem. Kindly observe it. Same notation we are using for two indications. One is a phase constant indication, cos beta L, sin beta L term in the ABCD. And the other is that angle of parameter B and angle of parameter A. So this is angle of B that I'm going to highlight. Angle of B, and this is angle of A. Angle of B and angle of A. Okay, you tell me, for lossless line, how is the angle of parameter B? 90 degrees. The angle of parameter B is 90 degree for lossless line. And angle of parameter A is 0 degree for lossless line. So for lossless line, if you talk, you get this like cos 90 minus 0, it will be cos 90, 0. Second term will be completely 0. We get only first term like mod Vs, mod Vr by mod B for the lossless transmission line analysis. So for lossless line, so you can get this maximum power transfer capacity like mod Vs into mod Vr by mod Vc. Mod Vs into mod Vr by mod B. Okay, what is a B? What is the B formula for lossless line? What's the formula for B for lossless line? Anybody? What is the formula for B of lossless line? Tell me please. That is ZC sin beta L. JZC sin beta L. Long transmission line. Long transmission line. From the long transmission line, parameter B is JZC sin beta L. But you need magnitude, na? So it will come to be ZC sin beta L. Come ZC sin beta L. Yeah, next thing. You'll be assuming this Vs and Vr values are almost equal. Let us assume. Mod Vr value approximately equals to mod Vs. Let's say it is mod V. Let's say it is mod V. Okay. Then this Pmax you can write approximately here. Magnitude of voltage square by ZC into sin beta L. Magnitude of voltage square by ZC into sin beta L. Okay. What is it mod V square by ZC? That mod V square by ZC is nothing but SIL. Mod V square by ZC is nothing but SIL. So it is the ratio of SIL to sin beta L. SIL to sin beta L. SIL to sin beta L. Okay, next. See, how is the sine value? Sine of an angle. How is that value? It will be generally less than 1. Sine of an angle generally less than 1. If this value was generally less than 1, SIL by less than 1 is a value of Pmax. So definitely we can experience that Pmax will be greater compared to SIL. As sin beta L value was less than 1, as it is less than 1, and we have a more than 1 into SIL equals to Pmax. More than 1 into SIL is a Pmax. So Pmax will be greater compared to surge impedance loading definitely. P maximum will be greater compared to SI. So this is one very important observation you have to make. This is a comparison between the ideal and maximum power transfer capacities of the network. Ideal and maximum power transfer capacities of the network. This is a comparison. Comparison between ideal and maximum power transfer capacities of the network. Okay. Next, listen now. Why I'm discussing this means, practically speaking, always, the loading on the transmission line must be less than maximum power transfer capacity. That's for sure. Steady state stability limit. I am repeating the statement. Kindly observe. Power divided. Load what we are keeping on the transmission line should be less than steady state stability limit. Means should be less than the value of P maximum. That's for sure. See, in that sense, can I prefer to go for loading equals to SIL? Can I consider that loading is equals to SIL? Yes or no? Loading equals to SIL, can we choose or not? All of you, please tell me. Yes, we can choose because your SIL will be less compared to P maximum. SIL is less compared to P maximum means if you keep your loading equals to SIL, that will be less than P maximum only. So good stability is going to be maintained. Good stability is going to be maintained. Okay, right. So loading equals to SIL is suggestible. Suggestible. Can I go for loading greater than SIL? Loading greater than SIL. For example, for your understanding, I'm saying here. For example, for your understanding, Pmax number, let us say 1000 megawatt. Okay. SIL number, let's say 620 megawatts. How much is the loading I have to keep means you have to keep less than P maximum. Less than P maximum we have to keep. Less than P maximum means I can keep 620 megawatt as SIL number, or else I can keep above 620 also, right? Above 620, but should be less than 1000. Above 620, but should be less than 1000. Less than 1000. Okay. So, in order to utilize the transmission line effectively, the suggestion what we are making, for loading on transmission line is loading greater than SIL. Loading greater than SIL, but should be less than P maximum. Should be less than P maximum. But it may not be practical in all cases. It may not be practical in all cases. Okay. So I'll write here. So I'm writing here. Kindly observe. So for effective utilization of transmission line, loading greater than SIL will be suggested. But it should be less than Pmax. But it should be less than Pmax. It should be less than Pmax. Okay? But it should be less than Pmax. Yeah, done. Next. But this is not the final statement to keep the loading on transmission line, practically speaking. So according to the type of lines, we have short line, medium line, long line. These things we are going to consider separately, and we'll discuss what type of loading is suggested for short line, what type of loading suggested for medium line, as well as for the long line separately. So have a break for 5 minutes. So after this break, we'll be continuing with that types of lines and what type of loading is suggested for each and every line. Okay. So I have resumed the audio, video, and the screen. Resumed the audio, video, and screen. Okay. So now let's continue. First, I am taking up the short length of transmission line here. Short length of transmission line for length less than 80 kilometer, you can say. Length less than 80 kilometers. Listen. Length of line is less. So obviously, series inductive reactance is very, very low. Series inductive reactance is very, very low. So I can write the Pmax equation approximately mod Vs into mod Vr by series inductive reactance. Original equation is VSVR by ZC sin beta n. VSVR by ZC sin beta n. But approximately speaking, it is VSVR by X. VSVR by X. Okay, listen now. Listen, very simple. So as if the length of the line is very low, X value is very less, X value was very less, then obviously Pmax will be very large in value. Pmax will be very, very large. Pmax will be very, very large. Now, listen kindly. See, if you are interested to keep the loading based on P maximum value, if you are interested to keep the loading on transmission line by using P maximum, as P maximum looks to be very, very large, it says that we can go for a very, very high amount of loading. You can go for a very, very high amount of loading. But there is one more limit for loading on transmission line, that is thermal limit of the conductor. Thermal limit of the conductor, which we have not discussed till now. The starting class we said one time, but from that point onwards, we are attempting to keep the loading only on the P maximum value. But now I am recalling thermal limit. Why it is so means P maximum value looks to be very, very large for me. Okay, see, actually, we have to keep the loading on the transmission line with two limits. One is a P maximum limit. Next one is a thermal limit. P maximum value. Next one is a thermal limit value. Now, you should check these two values. First. And then, whichever is lower among the two, based on that, we should keep our loading. Then obviously, other limit will be satisfied automatically. Yeah, I will write the statement. Kindly observe here. So, as Pmax is very high, it is expected that Pmax, so-called steady state stability limit, will be greater compared to thermal limit. Greater than the thermal limit of the conductor. Okay, so to satisfy both steady state stability limit in bracket P maximum and thermal limit. It is necessary to keep the loading. On short transmission line, based on thermal limit. Based on the thermal limit. So to satisfy both P maximum and thermal limits, it is necessary to keep the loading on the short transmission line based on the thermal limit. So I think all of you getting this. Right. Because thermal limit is a lower value compared to P maximum. That's why we are taking up that. But if you go for higher and higher lengths, please listen to me. If you increase the length of the line, means if you are going for higher and higher lengths of lines discussion, X value is more, P max is less. Then P max Pmax value may come less than the thermal limit. At the time, based on what we have to keep the loading? Is it based on P maximum or thermal limit? Based on what we have to keep the loading? Is it based on P maximum or thermal limit? Tell me please. That will be definitely based on P maximum because that is low compared to thermal limit, right? So if you keep the loading based on P maximum, then definitely it will be lower than thermal limit also. The system is safe from damages. Safe from damages. So I can say next for medium length of lines. Medium lines. Medium length of lines. Okay. Look here. See, for medium transmission lines, loading is kept based on, loading is done based on voltage drop limit. A term like voltage drop limit. Voltage drop limit in the sense the ratio between the receiving end and sending end voltage magnitudes. Ratio between the receiving end and sending end voltage magnitudes, it should be in the gap of 0.95 to 1.05. You should set the loading on the medium transmission line such that the ratio between receiving end and sending end voltages should be lying in between 0.95 to 1.05. 0.95 to 1.05. In order to avoid the usage of compensation, in order to reduce the compensation requirement, we have to keep the loading based on the voltage drop limits, particularly for medium length of transmission lines. So you write if you want here to reduce the compensation requirement. Compensation requirement. To reduce the compensation requirement. Yeah. So I think you are okay with this. Next one. Next one. So I think my connection is well. I think connection is good. So please kindly confirm audio, video, and screen. Is there any lag you are experiencing? Is there any lag you are experiencing? Please tell me. Yeah, all fine. No lag. No lag. Okay, good. Next. Long transmission line, we should say. Long transmission line or long length of lines. Long transmission lines, or you can say long length of lines. See, as if length of line is very high, your Pmax value will come very, very low in number. P maximum value, if I take a maximum power transfer capacity, which is Vs into Vr by X. So X is very high, so Pmax is very, very low. P maximum value was very, very low. Okay. Pmax is very, very low. See, definitely if you are thinking about long transmission lines, we have to keep the loading only on the basis of the maximum power transfer capacity, so-called the steady state stability limit, in order to maintain good stability for the system. So always long length of lines are loaded based on P maximum limit or steady state stability limit. Steady state stability limit. Next thing. So let's think about this long line little bit more. Particularly, I'm talking about EHV lines and UHV lines. Into that, moreover, 400 kV and 765 kV lines. I'm discussing about only for 400 kV and 765 kV, very long lines, maybe of 300 kilometers, 250 kilometers in that range. Look here. For 400 kV, 765 kV long transmission lines. long transmission lines. This is a small heading I am considering. Small heading I am considering. Kindly observe this. Kindly observe this one. See, this is that transmission line we have connected to grid, or you can say infinite bus, whatever. Connected to grid, or you can say infinite bus line transmission. See, definitely, if the 400 kV line, if you are talking, 400 kV line, if you are talking, we have one transformer here, and there is a generator also. Set of generators. I am showing only one generator. Look, stop writing, please. Stop writing, please. Just listen. Just listen. This is one section, so-called only transmission line. Only transmission line section. For this transmission line, having a maximum power transfer capacity of P maximum 1. For the transmission line, what we have chosen, that line will have a P maximum value, P maximum 1. P maximum 1. How is the P maximum and SIL comparison of transmission line? How is the P maximum and SIL comparison of the transmission line? Kindly listen. Kindly listen. Just now we discussed and compared it, right? P max is greater than SIL. So we have SIL for this line, and P max 1 is greater than SIL of the line. P maximum 1 is greater compared to SIL of the transmission line. Definitely. Definitely. Yeah. Listen to the question. Listen to the question. But if you are thinking about loading on this system, what you have drawn on the paper, if you are thinking about loading on this system, based on what maximum power transfer capacity we should keep the loading? Based on what maximum power transfer capacity we should keep the loading? Is it the P maximum 1 value, or is it the P max of the whole network starting from generator to infinities? I'll show this P maximum as something like P max 2 whole network P maximum is P maximum 2. Based on what P maximum we should keep the loading? Is it P maximum 1 or P maximum 2? P max 1 is only for line. But we are keeping loading on the network, so-called loading on the generator. We should consider starting from generator to bus bar, generator to infinite bus, what you have, our grid. So P max 2 is a thing based on which we should keep the loading on this one. P max 2 is a thing which we should choose to keep the loading on this one. Listen please. How is P max 2 compared to P max 1? How is P maximum 2 compared to P maximum 1? Less or more? Definitely less. Why it is so means this generator reactance, transformer reactance will be added to line reactance. Overall reactance will be increased. So P max will be less. So P max 2 will be less comparing to P maximum 1. So I'll write here. Loading on above circuit or above system. Loading on the above system shall be done based on P maximum 2 value. Shall be done based on the P maximum 2 value. Okay. Yeah. Next thing. Listen please. This is a type of logical thing you have to understand. Logical thing. Easy only. Just listen. P maximum 2 is less than P maximum 1. We have to keep the loading based on P maximum 2 means less compared to P max 2 we should keep. Less compared to P max 2 we should keep. If you are keeping loading less than P maximum 2, is there any chance of getting the loading less than SIL of the line? P max 1 some number, SIL some number. SIL is less compared to P max 1. Okay, SIL of the line, let's say some value 400 megawatt. 400 megawatt is a SIL. And P maximum 2 something like 500 megawatt. And you have to keep the loading based on P maximum means less than P maximum 2. If you are keeping it less than P maximum 2, it may fall below the surge impedance loading of the line. Maybe. Yes or no? Yes. So while you are keeping loading on this whole system based on the P maximum 2 value, loading on this particular system means particularly line you talk now, line. Loading on the transmission line might come less than its SIL, less than its SIL. That's why to maintain good stability, for the system, particularly for 400 kV and 765 kV lines, 400 kV and 765 kV lines, loading less than SIL is more practical. Loading less than SIL is more practical, right? So that implies, right? Loading on transmission line, might be lower than its SIL. Therefore, for 400 kV, 765 kV long lines, long length lines, loading less than SIL may be, or loading less than SIL, not maybe, is practical. That's it. Is practical. Loading less than SIL is practical. So do you experience any Farad effect for 400 kV and 765 kV lines now? Do you experience any Farad effect for 400 kV and 765 kV lines? Yes or no? Yes, practically we get Farad effect for 400 kV and 765 kV lines. That's why practically we keep the shunt reactor banks at the levels of the 400 kV and the 765 kV, because loading is less than SIL means receiving end voltage will be greater compared to sending end voltage. Okay, as a single question, maybe in interview you can say, some people might ask you, which type of loading is practical on overhead lines? What you have to answer? Which type of loading is practical on overhead lines? What you have to answer now? Which type of loading? Is it loading equals to SIL, more than SIL, less than SIL? Which is practical? All the three will be practical, na? All the three will be practical. It depends upon the length of line. Particularly for 400 kV and 75 kV long length lines, loading less than SIL is practical. Medium lines, you are forcing the voltage to be kept in these limits, right? Medium lines, you are forcing the voltage to be kept in these limits. Means you are attempting to keep the voltage close to 1 per unit. Keeping this ratio close to 1 per unit means your aim is to keep mod VR close to mod VS. If you are attempting to keep mod VR close to mod VS, you should go for loading equals to SIL. Loading equals to SIL in case of medium lines. In case of short line, as you are keeping based on thermal limit, loading might come definitely greater than SIL. Loading might come definitely greater than SIL. So based on the length of transmission line as well as operating voltage levels, which loading is suggested, we are going to take in practical system. So I think all of you understood this thing, what we have discussed. So if you are clear, I will discuss briefly about underground cable loading also. Can we have 765 kV short line? Yes, we may have. At that time, we should go for thermal. 765 kV short line may also be there. Maybe I will tell you one situation. Not 765 kV. I'll tell you about 400 kV line. 400 kV line. There is a power plant nearby Krishnapatnam. Krishnapatnam power plant we have, right? Thermal power plant. And nearby this Krishnapatnam, I think around 40 to 50 hardly, 40 to 50 kilometers hardly, we have one 400 kV grid there. 400 kV grid at a location called as Manugolu in Nellore district. This Krishnapatnam is also in Nellore district only, in AP, Andhra Pradesh. See, the distance between this power plant and this 400 kV grid is hardly, I think, 40 to 50 kilometers. 40 to 50 kilometers. So I have to run a 400 kV line now. I have to run a 400 kV line. So this 400 kV line, it's of only 40 to 50 kilometers. 40 to 50 kilometers. It's a short line with respect to length. With respect to length, it's a short line, but voltage level is very high. Voltage level is very high. This type of line, we should load based on thermal limits. This type of line, we should load based on the thermal limit rather than looking at the P maximum. So this line has to be loaded based on, it has to be loaded based on, loaded based on thermal limit. Krishnapatnam, it's a thermal power plant. We have a Genco power plant there. AP Genco power plant, thermal power plant. Yeah. So this is one of the practical examples what you can do. Short lines may go for loading greater than the same. So this plant is an exception of definition of short line. Yes. This is more length. That is a difference. Is not why you are calling here. Yeah, thermal limit based on its length, I said already. Okay, let's continue with UG cables, loading on underground cables. Loading on underground cables. Loading on underground cables. Yeah. See, first you tell me regarding the cables. How is the surge impedance of cable? How is the ohms, something 40 to 80 ohms we have said earlier. 1 minute please. See, ZC of the underground cable is very, very low in number. For example, you take a cable like this, and the surge impedance of this cable I am taking 40 ohms only. Typical value. Voltage rating 400 kV. Voltage rating is 400 kV. Then what's the SIL of this cable? SIL of this cable is rated voltage square. Rated voltage is square by surge impedance. And this will come like 4,000 megawatts. Come like 4,000 megawatts. 4,000 megawatts means look here, means SIL of the underground cable is 4,000 megawatt. That number itself looking to be very, very large. That number itself looks to be very, very large for you. See, if you are attempting to keep the loading based on this, loading is equal to SIL. Let's say loading equals to SIL. If you are keeping, how much power you have to transmit to the cable? 4,000 megawatt you have to transmit to the cable. It's a highly impossible case. We are sending that much amount of power, 4,000 megawatt. Definitely the cable is going to experience a thermal damage. Thermal damage. So we have to keep the loading on the cables on the basis of the thermal limit. On the basis of the thermal limit, and always loading less than SIL is practical for the underground cables. So I am writing the statement, kindly go through it. SIL of cable is very high. SIL of the cable is very high. If loading is done based on, or loading is equals to SIL is maintained on the cable, then the cable may experience thermal damage. Cable may experience thermal damage. Cable may experience thermal damage. Okay. So loading on cable done based on thermal limit, based on its thermal limit, and always loading less than SIL is preferable. Loading less than SIL is preferable on the cable. Preferable on cable. Loading less than SIL is preferable on the cable. Okay. Loading less than SIL is preferable on the cable. So I think all of you understanding this. All of you understanding this kindly. Yeah, what about P maximum means already in TH we said P max is greater than SIL, right? P max value was greater compared to SIL. So there is no topic of P maximum now. Yeah, SIL itself is very large and your P max will be very, very high compared to 4000 megawatt. Even loading equals to SIL is it is unable to sustain. Yeah, so let's continue. So almost we completed the steady state analysis. Almost we completed. One last topic left here for studies in the steady state analysis, which is also important for examination. That is equivalent lumped models of the transmission, long transmission. Equivalent lumped models means equivalent pi and equivalent t models of the long transmission line, which we will be using in the load flow analysis for the replacement of the long. Yeah. So let's take up the next heading, next topic here. It's a very short one. We'll discuss one or two problems on this and we'll quickly move. Equivalent models, lumped models of long transmission line, in bracket distributed model. Distributed model. Equivalent lumped models of long transmission lines, in bracket distributed model. First of all, for this uniformly distributed model, you know ABCD parameters here. ABCD parameters. I am writing original ABCD without taking that as a lossless. Original ABCD I am writing like cos H gamma L, ZC, sin H gamma L, 1 by ZC sin H gamma L, and then we have cos H gamma L. These are the original ABCD of the transmission line, long transmission line ABCD. Done. Next. First, let's take equivalent pi. Let's take here equivalent pi. Equivalent pi. Directly, I am taking the equivalent pi. I'll draw pi model first. Just pi model means I know we have a series element and we have shunt element extending inside, shunt element extending. That I will draw first. Later on, we'll think about those. So, in the equivalent pi, so we have pi model simply like this. Yeah, next, listen. Series element, it's not exactly series impedance. I'll call this is Z dash. And this is Y dash by 2. And this will be again Y dash, Z dash, Y dash by 2, Y dash by 2. Z dash, Y dash by 2, Y dash by 2. Equivalent by. Next thing. See, simply, I have to calculate the values of Z dash and Y dash by 2 here. I have to calculate the values of Z dash and Y dash by 2. These two numbers we have to calculate such that the ABCD parameters of this equivalent pi model and exact ABCD of long line both should be matched. Okay, fine. See, simple, very simple. What are the ABCD of this equivalent pi now? Equivalent pi ABCD will be A equals to D, A equals to be 1 plus z dash y dash by 2. That value we should make it equals to cos h gamma l. Okay. What is parameter B for this equivalent pi model? Z dash. What's the parameter B of line transmission line? ZC sin h gamma l. These two we should match. What is parameter C of equivalent pi model? Y dash into 1 plus z dash y dash by 4. That should be equals to the parameter C of line 1 by ZC sin h gamma l. Similarly, D also. By matching like this, we should calculate the values of z dash and y dash by 2 numbers. You have to calculate the numbers z dash and y dash by 2. Okay, tell me please. Tell me all of you. Tell me all of you. With what parameter we start doing the calculations? With what parameters? With what parameter we'll start doing the calculation? I'll take parameter B. Parameter B. What's the parameter B of model? Z dash. What's the parameter B of line? Line. ZC sin h gamma. These two we should match. First, I'll write. For model, B is equal to Z dash. Whereas for the line, B is equal to ZC sin h gamma L. These two we should match. Means Z dash value equals to ZC sin h gamma L. Z dash value is equals to ZC sin h gamma L. This is one value we got. Next thing. How to calculate y dash by 2? Anybody tell me please? How to calculate y dash by 2? I'll take A, parameter A. For model, what's A? 1 plus z dash y dash by 2. What is A of line? Line, cos h gamma. Those two we have to match. So I can say for model, A is equal to 1 plus z dash y dash by 2. Whereas, for line, A is equal to cos h gamma L. Cos h gamma. These two we should match. We should match means 1 plus z dash y dash by 2 equals to cos h gamma L, I can write. And y dash by 2, if you write from this, get it as cos h gamma L minus 1 by z dash. So you can get here cos h gamma L minus 1 by, what is that z dash? Parameter B. That z dash is parameter B, we can say. Parameter B. So this is a way of calculating, or you say z dash, no issue. Z dash or B, anything. This is a way of calculating the, what we call, is A na? A minus 1 by B. This is a way of calculating the y dash by y dash by y dash by. Okay. Next one, equivalent T model. Equivalent T model. It's a very simple one. Very simple one. What we are doing till now means in case of nominal T, nominal pi and all. We have taken a model. From that model, we found the ABCD. We have taken a model. From that model, we found the ABCD. But now what we are doing? We know already ABCD of line. We know already ABCD of line. This ABCD, by using this ABCD, we are constructing a model such that whatever the ABCD we calculate for the model, that should match with the ABCD of the line. Then only this model what we have drawn as a lumped will be representing the transmission line. Will be representing the transmission line. Okay, next. Equivalent T model. Quickly. Equivalent T model, we can say. So first let me show that T model here. Let me show this T model. Yeah. So like this we have T model. And this is y dash z dash by 2. And this again z dash. Y dash z dash by 2, z dash by 2. Yeah. Next thing. Next thing. So now again you take up ABCD of this T model. and already we know ABCD of line. Match them together and try to find out the values of Z dash by 2 and Y dash. With what parameter will start? Parameter C. Because in case of T model, parameter C itself is Y dash, and here the parameter C is 1 by ZC sin H gamma L. So obviously, whatever the parameter C we have for the line, that we should keep as a shunt element. Okay, so you write for model C is equal to Y dash. Yes, for the line, C is equals to 1 by ZC sin H gamma L. So from these two, we can call Y dash value is 1 by ZC sin H. By ZC sin H. That's it. Yeah, next. What is parameter A of model? 1 plus Z dash Y dash by 2, and for line, long line, cos H gamma L. Those we have to match, and we should get this Z dash by 2. That's right. That's right. So parameter A, 1 plus Z dash Y dash by 2. This is for model. This is for model. Whereas for the line, you know, parameter A is cos H gamma L. This is for the line. So match these two. So you can get 1 plus Z dash Y dash by 2 is equals to cos H gamma L A. So from this, you can get this Z dash by 2 like cos H gamma L minus 1 by what you get? Y dash. Right? So you can write this like cos H gamma L minus 1 by Y dash is what? 1 by ZC sin H gamma L. 1 by ZC sin H gamma L. Okay, see, like this, you have to calculate the values of this Y dash and the Z dash by 2. Y dash and the Z dash by 2. Yeah, please tell me all of you. Please tell me all of you. So I think all of you have understood the procedure. Please kindly respond. Have you understood the procedure and the thing what I am discussing here? Please kindly tell me. Have you understood the thing what I am discussing? Clear? Yeah. Now the thing what I am saying is very simple, very simple. What are the ABCD of equivalent pi? What are the ABCD values of equivalent pi? Anybody? Anybody? What are the ABCD of equivalent pi? Cos H gamma L, ZC sin H gamma L, 1 by ZC sin H gamma L, cos H gamma L, na? Such that we are setting the values of Z dash and Y dash by 2. Such that we are setting the values of Z dash and Y dash by 2. That's the thing we have to understand. What are the ABCD of equivalent T? Same, cos H gamma L, ZC sin H gamma L, 1 by ZC sin H gamma L, cos H gamma L. Such that we are setting the values of Z dash by 2 and the Y dash. Okay, so this model we will be using for the replacement of the distributed model in the load flow analysis. So I think all of you getting this thing what we have seen. So now we will take up some problems on this. Some problems on this one. Yeah. So let's see. So this is a question from our classroom practice questions only. Go through this one. Go through this question once. Here. So a lossless long transmission line rated to operate at 50 Hz frequency. Rated to operate at 50 Hz frequency of length of 400 kilometers. 400 kilometers. The surge impedance of the line is 1 per unit. Surge impedance is given in per unit form. That you should be careful. 1 per unit. Surge impedance is given as 1 per unit. Okay, next. Velocity of the wave propagation given as 3 into 10 power 5 kilometer by second. Velocity of the wave 3 into 10 power 5 kilometer by second. If the line was represented as equivalent T model, in its standard representation, means series element is in the form of impedance, shunt element is in the form of admittance. That's the meaning. Okay, yeah. Then the magnitudes of X and Y shown in the figure are. What are the magnitudes of the X and Y shown in the figure? Simple question. According to the statement, first statement is, he said the line is a lossless. So this makes the problem very, very simple. Line is a lossless line. It makes the problem very, very simple. Frequency how much? 50 hertz. 50 hertz is the frequency. Okay, next thing. Length of transmission line 400 kilometers. Length of transmission line is 400 kilometers. Next thing, surge impedance is 1 per unit. ZC you can take 1 per unit. 1 per unit. Velocity of the wave propagation 3 into 10 power 5. 3 into 10 power 5 kilometers by second. 3 into 10 power 5 kilometer by second. If the line was represented as equivalent T model, okay, in its standard representation, magnitudes of X and Y. So he has given that equivalent T model in this manner. Let me copy that model what they have given. Like this, we have the equivalent T model. Done. Simple, very simple. See, to find out this X and Y, first we should find ABCD of line. ABCD of line we have to calculate. What are the ABCD of line? Line, not for model. Not for model. You say for line, Parameter A and B equal cos beta L. Parameter B, JZC sin beta L, lossless line. Lossless line ABCD I am calling. Parameter C, J1 by ZC sin beta L. These are the ABCD. But you know, already we have experienced this. You know, in case of T model, only parameter A and C calculations are sufficient. Parameter A and C are sufficient. Because at C, whatever we have, itself is this shunt element. Itself is a shunt element. Okay. So I will go with this. First, I'll write for model means for this one. For model, C is equal to Y. C equal to Y. Next you write. For line, C is equals to J 1 by ZC sin beta. J 1 by ZC sin beta. What is ZC? 1. ZC is 1. Length 400. What is beta? Beta. What's the name of beta? Phase constant. Na? Beta is nothing but phase constant. What's the formula for beta? Omega root LC is a formula. For beta, formula will be omega root LC. This is nothing but omega by velocity of the wave propagation. Omega by velocity of wave propagation. Because L and C values they are not given. That's why I'm going with the second choice, omega by velocity. Let's substitute the numbers. Omega velocity 3 into 10 power 5. See, numerator is in radian by second. Denominator is in kilometer by second. So it will come to be radian by kilometer. So it will be 1.047 into 10 power minus 3 will be radian per kilometer. 1.047 into 10 power minus 3 radian by kilometer. That you substitute here along with ZC1 per unit, so that we get the C value in per unit domain. C value you are going to get it per unit domain. So you can get that C here, J 1 by ZC sin beta L. Length is 400. So see, this beta is in radian by kilometer and this length is in kilometer, this overall will be in radians. Overall will be in radians. Be clear about this angle. Whenever you are finding sine of some angle, cosine of some angle, kindly check whether that angle is given in degrees or radians. Kindly check whether that angle is given in radians or degrees. Here this angle is in radians. Radians. Tell me how much is this C? How much is that C? Anybody calculated C? 0.4188. J 0.4188 per unit. 4067 or 4188? Check once, check once. $4065 or 40668. 0.406 per unit. That's the parameter C. Next thing. See, already we said for model that parameter C is y, so the value y equals to that number. Therefore, y in that network will be J 0.406. J 0.406 per unit. Next, how to get this x value? How to get that x value? We have to go with parameter A. We have to go with the parameter A. What is parameter A of line? Per line. Cos beta n. Let's calculate that first. For line, transmission line, parameter A is cos beta n. Means we can write cos beta L 400. Again, this angle is in radians. Cosine of this angle in radians. Tell me, how much is that A? Parameter A, anybody? It's a lossless line only, Abhijit. Abhijit, it's a lossless line, no? Cos H gamma L written as cos beta L. It will be 0.9136. 0.9136. 9136. That's the parameter A. Now, what is the parameter A for model? For model. For the T model, what they have given. How is the parameter A? Parameter A. That will be 1 plus xy. 1 plus zy by 2. Na? Zy by 2. Actually, if you compare this with your original T model, this is y dash, this is z dash by 2, and this will be again z dash. So it will be 1 plus z dash y dash by 2. 1 plus z dash y dash by 2. And the z dash by 2 you can replace with x. So it will come 1 plus xy. 1 plus xy. Parameter A will be simply 1 plus xy. So that number 1 plus xy is equal to 0.9136. So the value x you want, right? X is equals to 0.9136 minus 1 by y. Y value just now we have got J 0.406. So get this number x, how much? Get that number x, how much? J 0.212. Positive J you get. Kindly check once. You will get this as positive J. Positive J. J 0.21. Now what's your answer? He's asking magnitude of x and magnitude of y. Na? X is 0.212. Y is 0.406, 407 close. Option A is correct. Correct answer from the options will be A. Correct answer from the options will be A. Clear? Okay, so let's say in the next slide, next problem, simple problem I'll take. Yes. It's a lossless transmission line. This problem is a lossless transmission line. Just go through it. See, a lossless transmission line of 400 kilometers length. Lossless transmission line of 400 kilometers length has series impedance and shunt admittance values per kilometer. Series impedance and shunt admittance value per kilometer as small z, J0.36 ohms, small y, J4 microsiemen, mho. Okay. If the sending end voltage of the line is 765 kV, what is the line to line receiving end voltage under no load? What is the line to line receiving end voltage under no load operation? If the line is not lossless, it's very laborious. You have to deal with hyperbolic cosine and hyperbolic sine values. Okay. Let's continue. Let's continue with this. Please tell me. Lossless line we have. Solution. The line is lossless. Lossless line. Length of line is 400 kilometers. Length of line is 400 kilometers. Series impedance J0.6, you can say, small j, J0.36 ohm per kilometer. Ohm per kilometer. Shunt admittance J4 microsiemen. Micro means 10 power minus 6 Siemen per kilometer. J4 microsiemen per kilometer. Sending end voltage of transmission line is 765 kV line to line. 765 kV line to line. That's the sending end voltage. What will be the line to line receiving end voltage under no load condition? What will be the line to line receiving end voltage? Means under no load, first of all, under no load, VR0 receiving end voltage is equals to Vs by A. Under no load condition, VR0, no load voltage, is equals to sending end voltage by A. So if you want to get it in per phase, you keep the phase voltages here. If you want to get it in line to line, you can keep line to line also. Because it makes no difference. Multiplication of √3 on both sides will give same result. Okay, look this one. What is A? What is the formula for this parameter A? What is the formula for this parameter A? Say you have this Z and Y values, Z and Y values. So A, I will keep this as cos H gamma L. Cos H gamma L. Okay, what is gamma? What is gamma here? Gamma, it is root of small z into small y. So you can write this like square root of z, J0.36, y, J4 into 10 power minus 6. J4 into 10 power minus 6. So it will become J. You will get this value square root of 0.36 into 4 into 10 power minus 3. So I think it is 1.2 into 10 power minus 3. 1.2 into 10 power minus 3. That's gamma. Gamma. So it's only imaginary number, right? Pure imaginary number. Pure imaginary number. So the line is obviously lossless. So this you can write as cos beta L for this lossless. As of lossless, it will be simply cos beta L, because this gamma you can replace with simply with J beta. J beta. So obviously the value of beta will be 1.2 into 10 power minus 3 radian by kilometers. Radian by kilometer. That you substitute and you get the value of A, parameter A, you get A is equals to cos beta L, length is 400 and it will be in radians. Radians. Yeah, please tell me how much is that? What's parameter A? Tell me please. 0.99. Okay. degrees. Tell me how much is A? 0.916 you are getting. Any other number you are getting? 0.961 or 916? Check once, please. 0.886 somebody is getting. Check 0.88. What's the length of it? 4 and only. 4 and 0.886. This value was 0.886. Okay. So now you can say VR0 line to line magnitude is equal to VS line to line magnitude 765 kV VS line to line magnitude by parameter A 0.886. How much is this? How much is that you can have? Tell me please. What is this number? 862.46 kV. 862.46 kV. Is it? That's a no load voltage line to line. No load voltage line. So anyhow, we will be stopping at this point. We may not have a class tomorrow. Tomorrow we may not have a class. We may not have a class. Kindly check the portal. By evening they will update it. By this evening they will update it. Tomorrow we may not have. Day after tomorrow we will be starting with transient analysis. It may not take much time. Only 4 to 5 hours it's going to take. And then voltage control, that's also a small chapter, 6 hours maximum case. And then insulators, cables and distribution system. By the day of 9th September, we are going to complete the syllabus. Okay. So if you have any doubts, you can raise your hands now. You can raise your hands if you have any doubt.
Sir, in this sum, A equal to cos h gamma L, how you take as cos beta L, sir?
Gamma is J beta, right?
Yes, sir. And
Gamma is J beta.
That hyperbolic function, sir.
Please kindly listen. Gamma is J beta.
Yes, sir.
Cos of J beta, cos h of J beta L.
Okay, sir.
What you can write that in hyperbolic functions? That's what we discussed long back in ABCD parameters, right?
Sorry, sir.
Huh?
I didn't know that, sir. Sorry.
We have seen that ABCD parameters converted from lossy to lossless. We discussed some place long back. I will show you. Here you can see. Here we have discussed now.
Yeah, okay, sir.
Okay. Clear?
Yes, sir.
Any other doubt here, Vignesh?
No, sir. Thank you.
Yeah. Salman Khan.
Good morning, sir.
Good morning. Tell me, Salman Khan.
Sir, if in any question we have to answer up to 2 digits after the decimal.
Okay.
And we got the answer like 0.889. So then we can put it 0.89 like.
Yes, you can keep it.
We can keep it, no?
You can keep it. Yes.
Okay, sir. Thank you.
Bharat.
Sir, so for short transmission line, we are keeping the load will be less than surge impedance loading, sir, for safe operation.
What is it? Can you tell me?
For short line, we are keeping the load will be less than surge impedance loading.
For short line?
Yes.
Agile
not
said
short.
loading less than SAL.
For short lines and long lines.
For short lines, I have not mentioned about loading less than SAL anywhere.
That will be less than thermal limit,
Thermal limit, okay, thermal limit.
but thermal limit will be less than SIL.
Who said?
Okay. It won't
Have you
be.
mentioned anywhere?
Okay,
Thermal limit is very high compared to SAL.
okay, so I'll check that. So for
Thermal limit and SAL comparison, we have not done. Thermal
okay.
limit will be greater compared to SAL, definitely. Particularly, you talk about overhead lines.
Yeah, so overhead lines.
Not for cables, for overhead lines.
Okay, sir, fine.
Okay.
So if you are getting Ferranti effect anywhere in case of overhead lines, so to avoid that, we will be using the
Shed reactors.
compensation
Shed reactors. Yes.
in every case.
In every case. In every case means particularly that over voltage chance, over voltage you will be getting for EHV and UHV lines only.
Okay, sir.
May not feel for lower lines like 130 kV. For those lines, you may not get it.
Okay.
Okay.
Okay, sir. Okay.
Any other doubt you have?
No, sir. Thank you.
Ashish Raj.
Sir,
Tell me, Ashish.
that question of T means lossless or T model, sir, that there you written A is equals to 1 plus XY, sir. How?
XY. Yes. X is the Z dash by 2, right? A equal to 1 plus Z dash Y dash by 2.
Y dash by 2, yes, sir, that's
So it is 1 plus. What is Z dash by 2? X.
Oh.
Y dash by.
okay, sir. Okay, sir.
Okay.
Okay. Thank you.
Yeah. Shraddha.
Hello, sir.
Tell me, Shraddha.
Sir, in approximate power equations, we take alpha is equal to 0, but delta is also equal to alpha, right?
What is delta and what is alpha here?
In approximate power equations, we take A.
Okay. I understood your doubt. What is delta and what is alpha? Tell me.
Delta is angle of D and alpha is angle of A.
Capital delta. Capital delta is that. Delta will be 0. Okay. Now
Okay.
what's your doubt?
Okay, so that capital delta and this delta is different.
Different, no?
Okay.
Small delta is the angle between sending end voltage to receiving end voltage.
Okay, sir. Good. And sir, also loading on transmission line, we take VR square by ZL, but it is also equal to IR square into ZL.
Yes.
But in that case, loading becomes directly proportional to ZL.
Loading depends upon current as well as ZL, both.
Okay.
Voltage.
But the voltage will be independent of load.
Almost.
Okay.
Almost.
Okay. Got it, sir. Thank you.
Pragati.
Sir, 238. In this question, I understood how you took like KSG equal to 0. We have already got loading is less than SAL. So can we say that we'll keep a shunt reactor branch?
Yeah, you can say it.
That's it, sir. Thank you.
Anybody have doubts? Please raise your hands.
Sir,
Bala Vignesh, tell me.
sir, this sum is doing under lossless or lossy transmission lines. sir.
Lossless only, no. I think I have mentioned it in the question, lossless. Didn't mention?
No, sir.
But surge impedance 300 ohms I have given, no?
Yes, sir.
Surge impedance I have mentioned, right?
Yes, sir.
Surge impedance, if they are giving, obviously line is lossless only, right?
Okay, sir. Because you yesterday told we can use this surge impedance in lossy line also with
So
some
that is
modification.
characteristic impedance. That is characteristic impedance.
Okay, sir.
Characteristic impedance of a lossless line is called as surge impedance.
Okay, sir.
As we said already, surge impedance value, it's obviously lossless line.
Okay. Thank you.
Okay, yeah. Sivagopi.
Yes, sir. Good morning.
Good morning.
Long transmission, sir. Angular stability
I am not understanding you, what you are saying. Please kindly repeat.
For short transmission lines, it is more on thermal stability.
Okay.
For long transmission lines, it is angular stability.
Okay. What's the doubt in that?
My doubt is, can I say for long transmission lines, thermal stability also affects?
No, for long transmission lines, Pmax is coming very low compared to thermal limit, right?
Okay.
See, both limits you have to consider. Steady state stability limit as well as thermal limit, both we have to consider. There's no doubt about it. But if you satisfy the lower limit among the two, definitely upper limit is also satisfied, na?
Okay.
Understanding?
Understand.
So if you are going for long line, I am considering both limits, thermal limit as well as steady state stability limit. But steady state stability limit is lower compared to thermal limit.
Okay.
So if I keep the loading less than steady state stability limit, it will be definitely lower than thermal limit also. Then both limits will be satisfied with one statement.
Okay. The thermal stability limit means it will be delivered by the transmission lines.
Conductor size, conductor will have some melting temperature, right?
Melting point. Okay.
Melting point or melting temperature. So that melting point is decided by how much of current is flowing continuously in that.
With respect to timing,
That amount of current flow will be decided by the loading.
okay.
That we are saying as thermal limit in megawatts. Thermal limit in megawatts. Degrees of centigrade converted to megawatts by this process.
Okay. Sir,
Okay.
okay, sir. Sir, why medium transmission lines we are more concentrated on voltage drop?
I'm not understanding. Okay, exactly what's your doubt.
For medium
Voice is
transmission
not
lines,
clear.
for medium transmission lines, why we are more concentrated on voltage drop? Sir, can you
See, to reduce the compensation, I said already. Providing compensation on the medium transmission lines is not economical, strictly speaking, because how many medium lines we have? Bulk number, right? 130 kV lines, if you think outside. Each and every 130 kV by 33 kV substation will get 2 or 3 lines, 130 kV lines.
Okay.
So number of 130 kV lines, 33 kV lines are very large. So providing compensation is very difficult. So that you try to keep your loading close to SIL for those lines, such that VR will be close to VS, reducing the requirement of the compensation equipment. Reducing the requirement of compensation equipment.
Sir, in that case, why can't we do with the short line and the long line, sir? Because sometimes they also need the compensation, no, sir.
Hey, which line? Short line means which short line you are saying?
Overhead short line, sir. In medium line, you said to reduce the compensation, we are maintaining loading equal to SIL.
Yes, yes.
Similarly, why we
You
can't do
see,
in long line and short line, sir?
Long line, if you are going, you are loading close to SIL value, you may be touching the P maximum.
Yes, sir.
Then you will be having lack of stability.
Yes, sir. It will be marginally stable like that.
Yeah. So in that situation, we should not suggest to go for close to SIL in case of long lines.
Okay, sir.
Okay.
I see.
Yeah. In case of short lines,
Yes, sir.
also you are going to get a similar type of scenario. Thermal limit might be coming into action there.
Okay, sir.
Yeah.
Okay.
Tell me, Gopi.
Okay, sir, please.
That's it, Gopi?
Yes, sir.
Yeah. Sachin.
Sir, in page number 224.
Okay.
Sir, can you explain this graph in short? I have a doubt. Can we get exactly same value of VS and VR by using this shunt capacitor and shunt?
We have done one problem also, right?
Yeah.
275 kV line problem.
Okay.
We maintain both voltages equal by designing the capacitor bank.
Okay. Sir, can you explain these graphs one time? Because I have a network issue at that time.
See, actually, for the condition of loading greater than SIL, receiving an voltage is less compared to sending a voltage.
Okay.
Okay.
So,
but you do have a decrement in the voltage starting from sending end side to receiving end side continuously like
Yeah,
this.
yeah. This is linearly, no?
Not linear, exactly not linear. It will be
Okay.
non-linear shape only, but for convenience, I have shown this as straight line.
Okay, okay.
Okay.
And
Once
this
after keeping this shunt capacitor bank,
okay,
the new receiving end voltage I am making equal to sending end voltage.
okay, it's exactly same. Okay.
Exactly same, such that you have to design the compensator.
Yeah, yeah, yeah.
Okay. So
Sir,
after
and-
making that, if you check voltage on the transmission line, it won't be same again. So it will start decrease from sending end side. It will start decrease from sending end side and then touches to receiving end side voltage, which will be equals to Vs.
Okay, okay. And this is compensator used for all the lines, na, short, long, and medium.
Any type of line according to the control of the voltage, we have to provide it.
Okay, okay. Thank you, sir.
Same.
Hello, good morning,
Tell
sir.
me, sir. Good morning.
Sir, here in that problem, beta 2, phase beta is equals to beta 1 into under root k into 1 minus kc, and that is that formula.
Yeah.
Sir, if we will go for compensation, then that beta value is
Will
going to
change.
be less.
Yeah, will change.
Means if beta value is less, then cos beta will be high.
Beta value is less.
Then cos beta will be high.
Cos beta L will be high. Okay.
Means A will be high, means we can say that we
Current effect is
are
decreasing.
achieving voltage Vs is equals to VR. It
No,
is
no.
advantage.
Cos beta, how you can say Vs equals to VR by based on cos
Means,
beta L?
we are nearly achieving, nearly.
No, say. If you are thinking, if you are discussing about only cos beta L term, only cos beta L, you should say about no load voltage.
Okay.
Okay. So you are modifying beta, that's okay. You are changing cos beta L.
Means
Sin beta L is changing. ZC is also changing.
means increasing beta is advantageous or not? Means it will be provided
Increasing
less
beta is an advantage only. Increasing beta is an advantage only.
because the phase
No, decreasing beta.
is advantage.
Decreasing beta is an advantage, not increasing.
Means that beta L is the phase difference between VR and IR is less.
Phase difference between VR and IR.
BS will be
VR and
less.
BS under surge impedance loading condition
Okay.
will decrease. Yes.
Then it is advantages.
Advantage.
Okay, sir. Okay. Thank you, sir.
Yeah.
Sir, another doubt is, sir, here we are writing the percentage series compensation is XC by X line. But previously you said that for IS to be flow in the transmission line, each section means for let's suppose for 50 kilometer. Individually means in a distributed manner we are compensating. Means is there any practical example of that loading is such a way that IR is equals to IS and VR is equals to BS? Is it achieving?
Yeah, we will attempt to keep it.
Means we can achieve, but it is not the regular fashion in transmission.
Not regular practice.
Okay, means according to our requirement, like this KSU 0.3 or
See, maintaining number of capacitor banks is not that much easy on the transmission line. Particularly series capacitors, you have to install one separate station kind of thing there at each and every place on the line.
Yes.
It may come in future, definitely.
Okay.
Already we have some series capacitor stations by means of FACTS controllers.
Yes.
We have practically on the 400 kV lines and 760 kV lines. But providing a type of distributed compensation is not yet come into practice.
Okay.
It may come in future, definitely. Okay.
Yes. Thank you.
Yeah.
Thank you.
Swapnil. Do you have any doubt, Swapnil? Swapnil. Imtiaz, tell me, Imtiaz.
Good morning, sir.
Good morning.
Sir, I have one small load. Sir, receiving end power factor and load power factor both are same or different, sir?
Hello,
What
sir.
is load power factor here? 1 minute, Swapnil. Wait.
Okay,
What
sir.
is load power factor here?
Where, sir?
This blue color one. Huh?
Yes, sir.
What is receiving end power factor?
Cos phi r is receiving end power factor.
Combination of load and capacity. Load power factor means this power factor only.
Yes, sir.
Okay. What is receiving end power factor of line? Receiving end
Both.
power factor of line means combination of load and capacity.
Okay, means cos phi r is more than load.
See, if you have only load, that load power factor itself is a receiving end power factor.
Yes, sir.
If there is any other element added at that bus bar, then you have to sum up, take up a whole thing and you have to define the power factor.
Okay, sir. I got, sir.
Okay.
Hi, sir. Thank you, sir.
Swapnil.
Yes, sir. Hello, sir. I'm audible.
Tell me. Yeah.
Yes, sir. In yesterday question, sir, in which we have to calculate the capacitor rating of actually QC rating of the line. In that case, sir, we have to find delta, where we calculated delta by using P equation, sir.
Okay.
And sir, and we got about 28.42 like this value. But sir, if we calculate same delta by using this equation, like Vs is equal to A VR plus BIR, sir, I am getting a different value of delta.
How you got IR value there?
IR values are actually they given load.
That is load
From that
current,
we
not receiving end current of line.
okay, means receiving end current will be different because of line
Because
charging current like
capacity is
this.
added. No, capacity added means receiving end current is different, right? It's not
Okay,
exactly
okay.
load current.
Okay, because of this, we are getting different value. Okay, sir. And sir, another one doubt, sir. While calculating the charging current, we know the formula is V divided by XC. Sir, somewhere I read that if we have to find XC, then if a transmission line is single phase, then we have to take the capacitance value is CAB
Yes.
and three phase CAN. Sir, is this correct?
Per phase.
And in the three phase transmission line, we have to take
The
C.
per phase charging current in case of transmission line, three phase line.
Okay, and
In case of single phase line, you should take line to line capacitance.
Okay, sir. Okay, sir. Got it, sir. Thank you so much, sir.
So any other doubts, you can raise your hands, else we will close the session.
Sir.
Yeah, tell me, Balvinkesh.
Sir, in distributed compensation, always series compensation will be capacitor only, sir.
Actually, I will tell that in tomorrow class. I have to announce it strictly. So I will tell that in tomorrow class, Balvinkesh.
Okay,
compensation means it is an extra element we are adding to cancel the already existing one.
Okay, sir.
What is natural series element?
Natural series elements is inductor, sir.
So to cancel it, we have to add a capacitor.
That's only I'm asking, sir. Always it will be capacitor or...
If we said simply series compensation, it will be capacitor.
Okay, sir. Because here we found a percentage series compensation or which we found in for capacity.
Yes.
Okay, sir. Thank you, sir.
Hello, sir.
Tell me, Swapnil.
Suppose, sir, I have one doubt, sir, in the bundling of the conductor, sir. Sir, suppose we have bundling of the conductor. In that case, suppose, sir, in the single phase line, there is different current is flowing, sir. In that case, we have to take the distance raised to actual current. Means suppose in the transmission line, one current is flowing I1 divided by 3, and in second transmission line I1 divided by 3. Like this, current is flowing. Then, if we taking the distance in the formula of calculation of the inductance, in that case, sir, we have to take the power of the D as 1 divided by this fraction, sir. Is this correct, sir?
Okay, you can say like that.
Because,
are you getting the same thing what we have discussed?
Yes, sir, we are getting, but sir, suppose the current is flowing is different. I have to just cross check, sir. I'm not
Then
getting easy.
you consider that radius itself, no? Because in the bundle conductor, two subconductors are there having unequal radius.
No, no, sir, not an equal radius, sir. I'm saying that current flowing is different.
No, actually,
We intention.
Swapnil, listen.
Yes, sir. Yes,
If
yes, sir.
two conductors are there with the equal radius consisting only in one phase.
No, sir. I'm not saying like that way, sir.
Ah.
Suppose there is bundling of the conductor. In one phase, there is suppose 4 conductor, and
This is
second
phase
phase
A.
there.
Phase A.
Yes.
Okay, 4 conductors. Next, tell me.
Yes, and in the sir, suppose sir, current is flowing in the first conductor is suppose like different current, means suppose.
Yeah, listen, stop.
Yes,
If
yes,
all
sir.
all the 4 conductors are having equal size,
Yes, sir.
then definitely
Yes,
each and every one will carry I/4 current.
Okay.
Because all are running in parallel.
But
no?
sir, suppose. Yes, sir.
All are running in parallel, connected to same bus bar, right? Current
Okay.
is getting divided equally.
Okay, sir, suppose we take like that first conductor is having a different property, and we suppose a flow current I/6 in the first conductor, and
Then
in the yes, material
sigma
different.
will decide it then.
Yes, sir, and we take the intentionally like that in the first in bundling of the first phase. There is 2 conductor. In first conductor, there is a flowing current I/6, and second conductor current is flowing 5I/6. We
Are you changing
intentionally
material or same material?
sir, we changing material, because of this maybe current are
Okay, if
flowing
you are
different.
changing material, listen.
Yes,
If you are changing that material, according to the
Yes.
material sigma value, the
Yes,
current
sir.
will be flowing.
Yes, sir. And suppose
Based
sir,
on
we
that,
have
we have to calculate the what we call GMR.
okay. Then sir,
There we
we
should
can
go for the calculation of flux linkages, inductance.
okay. Based
From that
on that,
inductance equation, you get the GMR.
okay. Okay, sir. Means I can calculate sir generalized formula, sir. Is
No.
it correct? Can I ask?
No.
Okay.
For example, again, if you change the conductor size or conductor material, again we have a new GMR, right?
Okay. I just okay, sir. Okay.
Yeah.
Okay, sir. Thank you.
Okay. So, any other doubts? Please raise your hands. Suppose. Okay, I think nobody's having a doubt.